All right, we're getting to the last third of this chapter, and in this part of the chapter, we're going to be talking a little bit about graphing trig functions. So we talked in the last section about periodic functions, and we're going to talk today about how to graph those periodic functions, specifically sine, cosine, and tangent. We're going to look at the graphs of the other trig functions, cosecant, secant, and cotangent, but our focus will be on sine, cosine, and tangent. So the new vocabulary you need to be on the lookout for is amplitude and frequency. We'll see if we get to the frequency part in the video or not. So we're going to start with sine, cosine, and tangent functions. This is the main focus. Remember that periodic functions have repeating patterns, or sometimes they're called cycles, and the horizontal length of that cycle is called the period of the function. The amplitude, this is one of your new words, of the graph of sine or cosine is half the difference between the maximum and minimum values. So if I look at this graph down here, this is the graph of the sine of theta. Theta is like my x-axis here. Y is just my y-axis. So notice at the sine of 0 is 0, the sine of 90 is 1, the sine of 180 is 0, the sine of 270 is -1, the sine of 360 is 0. That's how they're getting those points. The amplitude here is 1. The highest point that sine reaches is 1, and the distance to its midline, which in this case is the x-axis, is 1. So that's the amplitude. It goes up 1 above the x-axis, down 1 below. Up 1 above, down 1 below. So the total distance from the highest point 1 to the lowest point -1 is 2, but the amplitude, it's 1. It's just the distance from the midline to its maximum or minimum point. The domain of sine is all real numbers. Notice its range with no transformations, right? Goes from -1 to +1. So the biggest that sine can be is 1, and the smallest it can be is -1. Its amplitude, it's 1, and again, without any transformations, its period is 360 degrees. It repeats every 360 degrees. Cosine is very similar. It looks exactly like the sine graph. It's just shifted to the left 90 degrees because the cosine of 0 is 1, whereas the sine of 0 is 0. The cosine of 0 is 1. The cosine of 90 is 0. The cosine of 180 is -1. The cosine of 270 is 0. And the cosine of 360 degrees is 1. So again, the period is 360 degrees. That's how long it takes to repeat a cycle. Its amplitude is also 1, the distance from its midline to its highest or lowest point. It has the same domain and range that sine does. All real numbers for the domain and the range from -1 to +1. But of course, we can do transformations on sine and cosine graphs. So if I have a number multiplied in front of sine or multiplied in front of cosine, that number tells me the amplitude. Notice it's an absolute value, so it's just the value of that number without the negative sign. So the absolute value of A is the amplitude, and the period is determined by whatever is multiplied by theta inside of my function. So I have the sine of b times theta. I take 360 degrees, which is the original period of the sine function or cosine, and I divide by the absolute value of whatever that b is, and that will give me the new period. So if this is 3b, I divide 360 by 3, and I get 120 degrees as my new period. All right, so let's practice finding those two things for this function, y equals the sine of 1/3 theta. So first we'll look for the amplitude. My a value here is 1 times the sine. So my amplitude is just 1, so I haven't changed the height of my function. So now for the period, I do 360 degrees divided by b. b is the value that's being multiplied by theta inside of my sine function. So I do 360 degrees divided by 1/3, which is the same as multiplying by 3. So the new period of my function is 1080 degrees. That means it will take 1080 degrees to do one full pattern of the sine function. So you guys try that same idea here. All right, your answer should have been A. Again, my A value is 1 here, so the amplitude is 1. My period comes from doing 360 degrees divided by 1/2, which is the same as 360 degrees times 2, so a period of 720 degrees. All right, sorry for these bad pictures, but just a reminder of how this works. If I have A times the sine of b theta, or A times the cosine of b theta, B represents the number of cycles in 360 degrees. So that B tells me how many full cycles I'll go through in one period. So if I look back at this example we just did, this 1/2 means that in 360 degrees, I'll only do half of a cycle. That's why it takes me 720 degrees to do a whole cycle. If I have 4 times the cosine of 3 theta, that 3 means that I'm going to do 3 cycles, 3 full patterns in 360 degrees, so 120 degrees for one cycle. Basically what we do is we use the graphs of those parent functions at the very beginning of your notes, and then we use the amplitude and the period to adjust them, to make them higher or lower, and to shrink them or stretch them horizontally. We can also use the theta intercepts, remember theta is like our x, to help us graph. And I have this for you on your notes, but if I have y equals a times the sine of b theta, it's going to cross the x-axis, or the theta axis, at 0, 0, at 1/2 times the period, 0, and then at the period, 0. So those 3 ordered pairs will be on the x, or the theta axis. For cosine, it's 1/4 times the period, 3/4 times the period, 0. So those are 2 x-intercepts of the cosine function. So let's take a look at what our graphs could look like. So we're going to graph y equals the sine of 3 theta. In this case, we're going to find the amplitude, which is 1, because my coefficient of sine here is 1. So my maximum value will be 1 and minimum will be -1. To get the period, we do 360 degrees divided by 3, 120 degrees. And then we're going to do our intercepts. So if you look at your chart, we're doing a sine function here. So I'll have 0, 0, half of the period 0. So since my period is 120 degrees, half of that is 60. So 60 degrees 0 will be another x-intercept. And then I do 360 degrees over b, which is the period 0. So I'll have another point at 120 degrees, 0. And then we take a look at our graph. So I start at 0, 0, the sine of 0, 0, go up to 1, and down to -1. But I have to graph those intercepts. So here I have my intercept at 60 degrees, 0, 120 degrees, 0. And then I would get back up to where I started. So, well, no, sorry, here is actually the end of one period. And then I just repeat that 2 more times in my cycle of 360 degrees. So having those points to help you graph is really important. So if I have 1/2 times the cosine of theta, this time my amplitude is going to change, right? That's my a value. So the amplitude is 1/2. It's a vertical compression. So it's only going to go up to 1/2 and down to -1/2. My b value here is 1. So I do 360 degrees divided by 1. So one period is 360 degrees, just like normal. And I can do my x-intercepts for cosine. It's 1/4 times the period, 0. My period here is just 360 degrees, so 1/4 of that is 90. So I'll have an x-intercept at 90 degrees. And then again at 3/4 times the period, which is 270 degrees. So take a look. Notice that the highest point here, the starting point of my cosine graph, there's not really a starting point, I shouldn't say that, but my y-intercept is 1/2. And then I have an x-intercept at 90 degrees and at 270 degrees. I know that halfway between those, it will hit its low point of -1/2. And then at 360 degrees, it will come back to the same height as that y-intercept. So I have one cycle in that 360 degrees. And all of those points help me graph it. Notice that my highest point is 1/2 and my lowest point is -1/2 because of the amplitude. All right, so I want you guys to try this one. All right, your answer here should be A. And so my amplitude is going to be 1. My period is 180 degrees, so I should do one full cycle of the sine graph in 180 degrees. So your answer here is A. Don't get it confused with B. In B, the height is 2, and my height needs to be 1 because that's my amplitude. All right, try this one. Your answer for example 2 part B is again A. Notice that my amplitude is going to be 3. My period is 180 because it's 360 degrees divided by 2. It's 180 degrees. And then if you want to, you can find these intercepts. That would help you. You should have an intercept here and here. And here are the actual points. That would be your y-intercepts, 45 degrees 0 and 135 degrees excuse me, 0. All right, we're going to move on actually to example 4. And example 4 is about tangent functions. Tangent functions have a very different shape than sine and cosine because tangent functions have asymptotes. So the parent function looks like this, y equals the tangent of theta. The x-axis is still our theta axis. Its range this time is all real numbers because it goes forever in the positive and in the negative direction. Notice that it does not have an amplitude because it goes forever in the positive and negative direction. Its domain is theta such that theta cannot be 90 degrees. Notice that here it's undefined. And it's every 180 degrees after that. So it's 90 degrees plus 180 degrees is 270. That's another undefined point. Plus 180 degrees is 450 degrees, another undefined point. So the way that we write that is 90 plus 180n. So starting at 90, then plus every multiple of 180, every integer multiple. After that, I have an asymptote. So I have infinitely many asymptotes and infinitely many of these curves in my tangent graph. The period is 180 degrees instead of 360, so it only goes from 90 degrees to 270 degrees. It's undefined at those two places, then it's undefined at 450. So every 180 degrees, that pattern repeats. And here are the theta intercepts in one cycle. 0, 0, half of 360 degrees over b, 0, and 360 degrees over b, 0. There is no amplitude. My period is 180 degrees over b, over the absolute value of b. So remember, my period is different for tangent. And my asymptotes are odd multiples of 180 degrees over 2 times b. So in this case, my b is 1, right? So 180 degrees over 2 times 1 is 90 degrees. That's where my asymptote starts, at 90 degrees. And in both directions forever, it's odd multiples of 90 degrees. So 90 degrees times 1, 90 degrees times 3 gives me 270. 90 degrees times 5 gives me 450, and so on. So let's take a look at this graph. We have the tangent of 1/2 of theta. To get the period, again, for tangent, it's 180 degrees divided by b. So 180 divided by 1/2, which is 360. And then to get my asymptotes, I do 180 degrees divided by 2b, going back to that formula. So 2 times my period is 1/2 times 2, so 1. 180 degrees divided by 1 is 180 degrees. So that's where my asymptote is going to start, and it's going to be odd multiples of that. So this time, since my period is stretched out by twice as much, my asymptotes are also stretched out. So look at what the graph would look like. So instead of having an asymptote at 90, I'm going to draw my first one in here at 180 degrees. And then it's going to repeat every odd multiple, right? So I have negative 180 degrees. Then here's the one we can see on the graph, 1 times 180 degrees. 3 times 180 degrees. Remember, it's odd multiples. And so on. At 900, that's 5 times 180 degrees. So I draw those in. And notice that now they're 360 degrees apart because of that 1/2. That was a horizontal stretch. So I draw in my tangent graph every 360 degrees using the asymptotes as my guide. All right, you guys try graphing this one. Okay, you should have gotten C. All right, so my period here is 60 degrees. The asymptotes will be odd multiples of 30 degrees. So negative 30 degrees, 30 degrees, 90 degrees, 150 degrees, and every 60 degrees after that. All right, these are what some of the other trig functions look like. Notice that here in red, they show me the graph of sine. Cosecant, the cosecant graph, kind of comes off of the bumps of the sine graph, and it has an asymptote wherever the sine is 0, because I do the reciprocal of 0 and I get something undefined. Same thing, here's my cosine graph. So the secant graph comes off the bumps of the cosine graph and has asymptotes wherever cosine is equal to 0. The cotangent graph looks a little bit like a reflection of the tangent graph, but not exactly. It has asymptotes wherever tangent would have been 0. Remember that cosecant is a reciprocal of sine, so 3 cosecant of theta is going to have the same period as 3 sine of theta, which is 3